आ गया बोर्ड आ गया। आ गया होगा ना। हाँ।
हाँ आगे।
Okay, so first let's just do the alpha particle scattering, right?
या।
So इसी को बोलते हैं रदरफोर्ड स्कैटरिंग एक्सपेरिमेंट।
हाँ हाँ।
उसकी उसके लिए जो द एक्सपेरिमेंट दैट डिड फॉर अल्फा पार्टिकल इज कॉल्ड एज रदरफोर्ड एक्सपेरिमेंट, and what it did was it led to the discovery of the nucleus
यस।
at the center of the atom. So this was the main reason it was done, or the main accomplishment. And इससे पहले जो था, if you remember, छोटी क्लास में होता है, there's a plum pudding model of the atom,
या।
right? So where there is a uniform positive charge pudding, and
राइट।
the whole pudding is positive, and you have negative uh,
हाँ।
electrons embedded in it.
हम्म।
Yeah. So the way you do this experiment is, what you do is you have some alpha particles with you, and alpha particle basically is positive charge 2, helium 4
या।
to 2 plus, 2
हाँ।
electrons are taken in, right? So it has 2 protons and 2 neutrons inside it. So you have a source of alpha particle which emits alpha particles,
हम्म।
helium 4 to 2 plus. And then what you have a gold foil, okay, a very thin foil, like aluminum foil is used for packing the food, keeping it
या।
hot. Similarly, you have gold foil, which is very, very thin actually. And these alpha particles come and target the gold foil. They come and strike it, okay? And then behind the gold foil, what you have is a detection screen where the alpha particles which pass through the nucleus,
या।
alpha particles come towards the nucleus of the gold atoms in the gold foil.
अच्छा।
So obviously, the gold is very heavy. It has a
यस।
lot of protons in it. So
हम्म।
as the alpha particles approach this heavy nucleus made up of positive charges, it gets repelled, depending on what is its distance, whether it is
हाँ।
directly straight towards the nucleus, slightly
हम्म।
above the nucleus, and so on and so forth. So basically,
अच्छा।
the uh, alpha particles get deflected. Okay. And
ओके।
uh, the, I'll show you the diagram, so nothing to worry. So there is a scattering of alpha particle that happens.
या।
Al- So the observation is most of the alpha particle will go straight.
या।
Okay, so there will be no deviation. They go straight through the foil with no most of them, which means even though you had a positive charge at the center of the gold atom, most of the atom was empty. So from
या।
that empty space, the alpha particles passed.
या।
Very few, some alpha particles were deflected at small angles like this because of the force of repulsion, and very, very few alpha particles, even less than, very small fraction, is which goes directly to the nucleus,
कम।
comes back. It goes with half mv square.
हम्म।
Complete half mv square gets converted into the electrostatic potential energy between the gold nucleus and the alpha particle. So alpha particle stops. So half mv square gets converted into k q1 q2 by r with a minus sign, with the electrostatic potential energy.
अच्छा।
Okay. So half mv square is equal to k q1, where q1 is the charge on the alpha particle, q2 is the charge on the nucleus of the gold.
ओके।
Okay, which is the number of protons will decide it.
या।
And these which are going directly to the nucleus, they come back.
अच्छा। या।
We say they have rebounded. It's like you striking a ball and the ball comes back.
ओके। ओके।
So
या।
these are the observations. Conclusions were very simple, that since most of the alpha particles pass through the foil with no deviation, that means most of the atom is empty.
यस।
Right? So imagine a very large atom with orbits, and at the center you have the nucleus. Now the alpha particle comes, it is not exactly towards the center, but away from the center of the nucleus. Right? So that means you start entering that space of the orbits. So you will pass through,
या।
because you will not get influenced by the nucleus.
हाँ।
Only when you're passing through the orbits which are close to the nucleus, will you get deflected by a small angle. And
Yeah.
if you're targeted right at the center of the nucleus, you will rebound. Okay.
Yeah.
So if you send 100 particles, 90 particles will pass through, so proving that the
Yeah.
atom is empty.
Empty, yes.
Right. It also proves that
Yeah.
because the rebound happened, it also proves that the nucleus is positively charged.
Yeah. Repulsion हो रही.
Repulsion, right? And
Yeah.
of course, what he also proposed one thing, that the electrons are not inside the nucleus. Electrons are orbiting around the dense nucleus, similar to
Yeah.
the planets orbiting the sun.
Sun. Yes.
And this was his Rutherford model, which Bohr picked up and started developing. Okay, but nucleus is at the center because most of the atom is empty, uh, and most of the alpha particles, sorry, pass through the atom, through the foil with no deviation. So the deviation of the alpha particle was very important in uh, deciding the nature of the atom. So nature of the atom was it is empty. At the center, it has a nucleus which is positively charged, and
Yeah.
electrons orbit around the nucleus.
Yeah.
They are not in the center.
Yes.
And finally, this resulted in development of your Rutherford, Bohr's atomic model. So Thomson,
हाँ.
Rutherford, Bohr.
Yes.
Rutherford. So Rutherford did an experiment, gold foil experiment.
Yeah.
So you get numericals on this. You also get theory questions also.
अच्छा, okay.
दोनों आते हैं. So you get either. Show you the diagram now. This is a diagram of some of the. You can see the diagram. So a stream of alpha particle is coming, right?
Yeah.
So the ones which are straight towards the nucleus, they rebound. The ones which are closer to the center of the nucleus, something like this, right?
Yeah.
Exactly at the center, gets deflected by a small angle.
अच्छा, yeah.
The farther you move from the nucleus, you can see the angle of,
Yes.
right? So
Yeah.
this is a huge deflection. I mean, if you go like this and turn like this is like a U-turn.
Yes.
But if
Yeah.
you go like this is less deflection.
Yeah. Yeah.
That is too much going U-turn. Right? So closer you are to the nucleus, more deflection you face.
Yes.
Right? Farther you are from the nucleus, you actually face no deflection.
Yeah.
This is hardly any deflection. You're way too away from the nucleus, so you face very little repulsion. Got it?
Yeah.
Okay. Excellent. So kinetic energy will get converted into the electrostatic potential energy. For the ones which actually, so this alpha particle, let me use a different color. So this is your directed at the center. Let's put it this way, this one, right? It stops here.
Yeah.
Now I'm just enlarging the diagram so that you can see what is happening. It has stopped there, right? So
Yeah.
here the whole kinetic energy has been converted into K, Q1, Q2 by R. And
हाँ.
this
Yeah.
small distance between the nucleus and the uh, alpha particle, which is stopped now, is called as distance of closest approach.
अच्छा, okay.
Distance of
Closest approach.
Okay? So how do you measure the deflection angle? This is the way you measure the deflection angle. If you're given a diagram and they say, please show us how the deflection is happening. So the theta angle, okay. Yeah. Look at this. So you can see, right, the alpha particle comes, and because it is away from the nucleus, it starts
Uh-huh.
getting deflected from here only. It starts feeling the repulsion from here, and then it goes along this the shape you see, right? So it is going like this. And
Yeah.
then if you want to find out what is the direction, what you draw a tangent on this curve, you get the angle of deflection.
Acha, okay.
How much it has turned, right? From its
Yeah.
would have loved to go like this, but because of repulsion, turns away.
Yeah.
Make sense? Any doubts
Yeah.
in your mind pertaining to experiment?
No.
What exactly is happening? Simple, eh? Not very
Huh.
complicated.
Yes.
Okay, let me show you. Uh, so it is only applicable that electrostatic energy formula only when the nucleus, sorry, the alpha particle stops
Hmm.
and comes back, which means only to the alpha particle
Acha,
which is
okay.
directed
Yeah.
to the nucleus, not because other ones still have a kinetic energy.
Yeah.
So they continuously have a electrostatic potential energy because of the interaction between the two charges, nucleus and the alpha particle, but also they have kinetic energy. So half mv square is equal to k q1 by q2, which is changing continuously because the distance is changing between them.
Yeah.
And I'm referring to the one which gets deflected. And the one which is
Completely
getting
different.
deflected like this also has a kinetic energy. But the
Yeah.
sum of energy remains same. Conservation is still maintained.
Acha, okay.
I will just, you understand conservation of energy? E initial is equal to E
Okay,
final.
fine. Yes.
Let's, let's do some. The electrostatic field is always conservative in nature.
Yeah.
So the real formula, which is not in your syllabus for finding the uh, differential cross fraction, I think you should forget it. You have this formula of closest approach, which is coming from, if you write, let me just show you what I'm referring to. So you have this numerical, for example, right? Read it first. Okay? So there is an alpha particle, it has some energy. Obviously, it has kinetic energy.
Yeah.
So this is your gold nucleus.
Take care.
This is your alpha particle. And because it is distance of closest approach, so the assumption is the alpha particle is directed straight towards the nucleus. Because this
Yeah.
term, distance of
Yeah.
closest approach, is
Take
only
care.
to
Take
be
care.
used, right?
Yeah.
Now, finally, what it does is it comes and stops here. So it comes and stops here.
Yeah.
And this distance is called as the distance of closest
First
approach,
approach. Yes.
right? So half mv square, which is the energy of the alpha particle, is equal to 7 million electron volts. And when it stops, right, it is stationary here. So its velocity is zero. So kinetic energy final is zero.
Yeah.
The alpha particle has no kinetic energy. So where has the energy gone? This energy gone. It has got converted into K
K Q.
Z E, which is Z for the gold, right,
Acha.
into alpha particle divided by R, the distance of closest approach. The distance between two charges is Q1, Q2. The distance
Yes.
is R, right?
Yeah.
The electrostatic potential energy is K, Q1, Q2, right?
Yeah.
What you can do is find the value of R. R is equal to K Z 2 E square by R. Make sense? Okay.
Yeah. Yeah.
Right. So this basically, sorry, I should have written. Okay. So this is half mv square, right? Sorry, on the left-hand side. I just substituted. This is half mv square. Just rub this off. Left-hand side is half mv square.
Uh-huh.
Although he has already given you the energy, you can straight away write it as 7 million electron volts. So you know K, you know 2, you know gold nucleus is 79. You know this is 1.6 into 10 raised to power minus 19. Or you have to find out and convert this whole thing, which will be in joules, into electron volts. Right?
2 क्यों लिखा है K2?
क्योंकि alpha is 2 plus
अच्छा, okay.
2 electrons, right?
Uh-huh.
And gold is 79e.
अच्छा, okay.
The charge on alpha particle, the charge in the nucleus of gold foil, one nucleus.
ठीक है.
Right? So generally they ask you, for example, what was the velocity? So half mv square is equal to k ze 2 e by r. So take this m on this side, 2 here, and you're left with v square, right? You're left with v square, right? So v
Yes.
is equal to 4 z e square k by r. Answer. If they give you the distance of closest approach is known, mass of electron is given.
Yeah.
Given this is known, k is known. You can find the velocity with which the alpha particle was moving towards the charge. Initial velocity. Final velocity is anyway 0. And during all this period here, for example, in middle, somewhere maybe at some distance which is known to you, the alpha particle has both the energies because it has slowed down. It slows down with
Yes. Yeah.
it has half mv final square plus a q1 q2 by r2, where r2 is this.
Equals to 0.
Now equal to same as the initial energy here. At energy at A
अच्छा,
equal
yeah.
to energy at B. Only difference is this energy now has got converted partially into the
ठीक है.
kinetic
Yeah.
energy and some part has been given to the potential energy. But overall remains same. The sum of these two will still be 7 million.
हाँ, okay, ठीक है.
It's a conservative field.
Yeah.
You don't lose energy in this. You lose it if you have, for example, friction. A car is moving on a frictional road, right? It stops. Because friction is a non-conservative force.
Yeah.
It wastes your energy. But, for example, Earth's gravity will not result in wastage of energy of the ball which you throw. It will get converted between kinetic energy and potential energy. Conservative. When the energy is wasted against something, that particular force is known as
non-conservative
or dissipative. Losing something. Dissipation.
ठीक है.
Okay.
Second.
That is correct. Just a repeat of theory in the form of MCQs. Large angle, something like a U-turn.
Second.
Yes. All other statements are rubbish, I think.
Yeah.
Atom is a solid sphere. No way. No, I never used the word sphere. Alpha particles are not negatively charged. conceptually wrong,
Yeah.
factually wrong. Electrons are uniformly distributed throughout the system. We never talked about electrons in this experiment. We just said they revolve around the nucleus like planets around the sun.
Yeah.
Why was gold used? Very important. High density, I don't think so. Malleability means you can use it to
Huh.
make wealthy, but you can't
Yes.
use it for experiments. Radioactive, I don't think so. I ever said it is radioactive. I didn't say that. I never said it's malleable. I never talked about its density actually.
Density. Yeah.
Although its atomic number, I mean, the number of protons it has is 79,
Huh.
very high.
Yes.
It is very high. So it can easily. Uh, but tell me, why was it used? I have said something. Okay, so remember, gold has can be easily converted into a foil,
Yeah.
which means it's very malleable.
Hmm.
Otherwise, you can't have a malleable.
Acha. Okay.
Yeah. So gold was used because it is highly
Very
malleable.
valuable.
Yeah.
Sure.
Foil, right? Foil means
Yeah. Yeah.
पतली सी होती है ना. So how do you make a foil?
Very small fraction.
That is correct.
I'm putting one.
Correct. So what was the secret to my asking you a question on vitamin D? Tell me. I asked you, have you taken a
Yeah.
lot of vitamin D? What was the secret? Vitamin D. क्या करता है वो?
पता नहीं.
You had sun exposure, right?
Yeah.
Sun exposure tans you.
Yes.
And when sun tans you,
Yeah.
you tend to hide your face.
हाँ. Yeah.
And therefore you don't switch on the camera. मैं सोच रहा था काफी टैनिंग लंबी चल गई है भाई, क्या हो गया? एनीवे, हाँ जी, देखो, मुझे लगता है मैं किसी आर्टिफिशियल इंटेलिजेंस को पढ़ा रहा हूँ.
नहीं, from next class and I turn on my
And it's
camera.
okay, it's okay. Whatever you're comfortable with, just follow your gut feel. That's all. That is fine.
Causes activation of alpha particles. A repulsion by the positively
Obviously,
charged
right?
material.
Obviously. Positive, positive. So,
High energy and positive charge.
yes. Wait. What is the question? Wait. Sorry, एक second. What property of alpha particle? Yes. Obviously, comes with a lot of kinetic energy. Yes. सही है.
What percentage? More than 99%.
Right. Majority. Correct.
Yeah. Third.
Yes. Okay, this I will tell you the answer. Good to know, but you don't need to know. Okay.
Okay.
It's a relationship between how much scattering. It's out of your course, but scattering. So it tells you the number of alpha particles. Like we said, 99% don't deflect, right?
Yeah.
So there is a formula for that. It is proportional to how much is a scattering angle. If you measure the scattering angle, you can find out the number of alpha particle out of 100 which get deflected at that angle. So every angle of deflection has corresponding number of alpha particle, not in our syllabus. The
Acha.
correct
Okay.
answer for this is if you have to decide the number of alpha particle based
Yeah.
on the angle at which they got deflected.
Yeah.
Then if the angle is theta, this is the correct answer. 1 upon sine squared theta by 2.
Acha. Okay.
So the number of alpha particle corresponding to an angle of deflection is proportional to theta like this.
Acha.
But you can put numerous values of theta, 1 degree, 2, 3, 4, 5, 6, 7, as many as you want. There's a
ठीक है.
complete formula for this. This is just to show you relationship between the angle of deflection and number. Right? So which means if you have 90 degree as the angle, right?
Yeah.
Deflection, which means practically like this.
Yeah.
Right? If you put 90 here, you will get 1 upon sine square 45.
Yeah.
Which is 1 by root 2 whole square. So this will become,
Yes.
and they may give you another angle of deflection, which could be, for example, 60 degree, right? So they may ask you to calculate the number of alpha particles at 90 degree and 60 degree. So
Yeah.
N1 was proportional to 2.
Hmm.
And now you can put 60 here, 30, right? So this will become 30 in the denominator. So that will be 1 by 2. So
Uh-huh.
sine square will become 1 by 4, 1 by 4, 4 will go. Right? So
Yes.
number of particles at less angle of deflection is 4.
Oh, yes.
Proportional to 4.
Yeah.
Right? So it's inversely proportional.
ठीक है. Yeah.
Good to know. If you don't know, it's fine. Right? So this finishes our topic number 1 in the syllabus.
Yeah.
The topic of alpha
Rutherford model.
and Rutherford. Both we have finished, right? What is
Yeah.
the next one? Let me see at the top. Yeah, I'm at the top now. Bohr's. Bohr's model of hydrogen atom. ठीक है? वो जो N1 is equal to 2, 3, 4.
अच्छा अच्छा हाँ.
What I will do is I will put the shells are there, right? KLM.
Yeah.
So if you just do so the way we look at this in physics is slightly different than chemistry, but almost all the formulas are same. Slightly different. Okay, so I think this is so this is electrons revolve around the Sorry, I think we are doing right. So, all right. So this is your Bohr's model. Okay, so at the
Yeah.
center is the nucleus. Then you have
Yes.
n is equal to this, and each orbit has, so inner orbit n1 is equal to has 2 electrons, then 8, 2, 8, 8, 2. Every orbit has a capacity of electrons. 2 n
Yes.
square, right? 2 n
हाँ.
square. वो केमिस्ट्री ओरिएंटेड पढ़ाई है, हमें उससे नहीं करना. So this is, so if you notice, it says that the energy of the orbit is increasing. The farther you are from the nucleus, more is your energy, more unstable you are. So valence electrons can leave also. They're not
Yeah.
very well
Yes.
bound
Yeah.
to the nucleus. If you're very good, if you have a very good binding with the nucleus because of the
हाँ.
electrostatic force, Coulombic force, right?
हाँ.
Then the energy is low because you're stable.
Yes.
As you go to the outer side, K, L, M, N, the energy keeps on increasing. But that is not what we need to really know right now. Okay. Later on, I think we do orbitals, right?
हाँ.
That the atom is not pure orbits only, but it's a space of electron, uh, negative charge around the nucleus, which is the cloud of electrons. Okay. Let's do the theory now.
ठीक है.
So we have just had a small look at, and we said the energy levels are there and energy increases, right? But let's come to the very bulleted points now. The first point you study about the model. You say, now, what are the key features of this model?
Yeah.
What are the key features? Okay, the first thing you have to know about this model is obviously the energy always. And let's expand on the concept of energy. So what Bohr said was this. So Bohr said the energy levels, okay, are quantized.
हाँ. Yeah.
Okay? Which means it is in multiples.
Yes.
Electron can only exist in certain allowed orbits with fixed energy.
Yeah.
Okay, so you cannot be anywhere. There are some values of energy which you have to follow.
Yeah.
Any electron you will pick up will have a certain value of energy.
Right.
Cannot have random. It has to have some value, and that is the concept of quantization. That you cannot have any level of energy. You will have some specific multiples of energy. Okay. So
Yeah.
every electrons orbit the nucleus in specific fixed energy levels of shells, rather than spiraling into a nucleus. So they don't spiral and fall in the nucleus. They don't. They don't fall inside by spiraling. You understand spiraling?
हाँ हाँ.
So electrons are in an orbit moving like this. They are not like this.
Yeah.
They don't collapse inside the
हाँ हाँ.
nucleus. They just continue to move. Okay. Okay. Second point. So these energy levels where it moves, the fixed energy levels are quantized, which means they are multiple of some number.
हाँ हाँ. ठीक है ठीक.
And the energy levels are denoted by 1, 2, 3.
Yeah.
So this is one. We'll come to the formulas also, right? Second, the second key feature is the concept of electron transition, which means the electron jumps from one orbit to another.
Yeah. Yeah.
Which means the different, and what gets emitted if you are from a higher energy to lower energy, is the electrons can move between energy levels
ठीक है.
by absorbing or emitting a photon.
Yeah.
If you absorb energy, you are at lower energy level, you will go to the higher energy level, maybe move to the different orbit. If you're at higher orbit, you will fall to a lower orbit
हाँ.
and release energy. And the energy is released in the form of a photon.
अच्छा, okay.
Right? So the formula
Yeah.
is this is my energy in the final orbit minus my energy at the initial orbit becomes a
Yeah.
photon. It can be absorbed also, which means I'm at a lower energy level, lower orbit, and I
Yeah.
want to go to a higher energy orbit. I will absorb energy. Light will come, I will absorb h nu. I will take a
Yeah.
photon and
हाँ.
jump to a higher orbit.
अच्छा, okay.
Third important point about Bohr's model is that he actually derived the expressions of energy, everything, radius of the revolution of the electron, etc., with the help of two concepts. Okay, because it's a circular motion, remember.
Yeah.
So the centripetal force is between the nucleus and the electrons. The electrons move in a circular orbits. Second is the centripetal force required is given by the electrostatic attraction, mv square by r. Right?
अच्छा,
If you
yeah.
have this nucleus and you have electron moving around it in a circle, then there is force between them, which is Coulomb's force.
Yeah.
Maybe some nucleus is there, say ZQ, right? And this is the electron. So ZE is the charge on the nucleus, protons.
Yeah.
E is the charge on this, and then orbit wherever it is. Maybe it's orbit 2, right? So I will say R2 is the distance, R2 square right now. This is the force between them, and it can be written as mv square by r. Right?
अच्छा,
It is
yeah.
moving in a circle. For
Yeah.
you to move in a circle, you need a force.
Yes.
It is coming from the electrostatic force of attraction.
Okay, ठीक है.
The electrostatic force of attraction is making it move in a circle. Tangent, right? Typical circular motion. Got it?
Yeah.
Okay. And similarly, there is a potential energy also between them, right? If somebody says what is a energy concept, right? Electrostatic energy. So this electron, which is moving in a circle like this. So let me just draw the circle here, right? So I will draw the circle. Let's say this is my circle, right?
ठीक है, yeah.
This is the circle. Now, if you say the electron is here, for example, right? At some distance from the nucleus.
हाँ.
So let's say this is my nucleus. It is at the center. This is the distance I have, right? This is the distance. Okay. This is the distance. So the electron has a velocity v in this orbit, which is fixed. So it has a kinetic energy half mv square. Because it is in motion, it will have kinetic energy.
Yes.
The kinetic energy of the electron in some orbit. We can write v nth orbit. Also, it has energy because of its interaction with the nucleus, which is K E Z E by R.
हाँ.
Right? And the force is attractive. So this is the total energy of the electron.
अच्छा.
This part is the potential energy because it is interacting with the nucleus, attraction, and this is because of its motion.
Yes. ठीक है.
So energy. Title was energy, right?
Yeah.
So energy and centripetal force, both are used. Now, very important, the first question actually that comes, wait. So another important feature of this whole theory is the angular momentum also is quantized. Okay, angular momentum is a class 11th concept. It is applicable here also, it gets used here. So what does it say? It says that energy is quantized, which means energy can have fixed values.
Yeah.
The angular momentum is also quantized. And what does it mean? What it means is that if you have a so this is your electron and revolving, and it has a velocity v here. This is its perpendicular distance from the center,
Yeah.
right? Its linear momentum is m into v. Okay, so I write it as mv. It's a linear momentum.
Yeah.
The angular momentum is calculated by, represented as L, is given by m r cross v.
Yeah.
11th standard concept, where r, the direction of the momentum is this,
Yes.
and perpendicular is drawn from the axis about which the body is moving. It's a point mass, remember. Electron is a point mass.
Point mass.
So it's a point mass. I'm not sure, is it V cross R or R cross V?
तो R cross V होता है शायद.
हाँ. वेक्टर प्रोडक्ट होता है, ये मुझे याद है.
हाँ, R cross
यूज
V.
नहीं करना वेक्टर प्रोडक्ट यहाँ पे. You don't need to use any of this. Only thing is good to know information. Some 11th standard revisions or to say, okay. Just checking what is exactly is the, it's R cross V. Okay. So sometimes in NEET examination, you get multiplication of two vectors. They give you R vector and V vector, and it's a point mass. So the perpendicular distance. So this is the direction of the linear momentum. And the perpendicular is drawn from this direction to the axis. And this perpendicular distance, which is dropped from the axis means about which you're revolving, the center. So you can see you've drawn a tangent, which is the direction of the linear momentum. And then what you have done is you have drawn a perpendicular from the axis to the direction of the linear momentum. So this is 90 degree always. So if you see anywhere, it will be 90 degrees. So for example, you considered this point, right? Let me show you one more point. This is a point, right? This is the direction of linear momentum.
Yeah.
Draw a perpendicular like this. So tangent and radius are always perpendicular.
Yeah.
10 standard circles. Right. So I'll just try and revolve it a bit. Okay. Now, the angular momentum is L is given by m r v sine 90, because the angle between them is always 90, between r and v. So it becomes mrv. This angular momentum of the point mass, which is your electron, is quantized, means it is always a multiple of nh by 2 pi. This is Planck's constant. This is orbit number.
Achha.
This is 2 pi. So angular momentum in the nth orbit, having radius rn and the velocity vn, is given by this. So electron cannot have a random angular momentum. It always needs to be n times h by 2 pi.
By 2 pi, yes.
Got it?
Yeah.
Okay. Now you have some sense of angular momentum. It's an important topic for NEET examination. Practice angular momentum questions. Okay. So we have done all, right? So we have done quantization of energy level as a feature only. We have not studied the theory behind it, the derivation. We know there is something called as electron transition which happens. So in any orbit, the energies are at certain level, and therefore it is quantized. The electrons transition between the orbits, they absorb energy and release energy in the form of photons. Then there is a centripetal force between nucleus and the electron, and there is a energy also, the total energy, which is quantized,
Hmm.
which is half mv square plus k q1 by q2 by r. And then the angular momentum is quantized.
Hmm.
Last feature of this theory is the concept of stationary orbits.
Okay.
What it means is the electrons do not emit radiations. Okay, so the
Hmm.
classical EM wave said EM waves are released by the charges which are moving. In EM, an EM wave is generated by a moving charge. We studied electromagnetic waves, right?
Yeah.
Okay, in that chapter, where does a wave come from? Obviously, one of the sources is sunlight,
Hmm.
but there are in that theory said that if you have a charge moving, it will
Hmm.
also emit EM waves.
हाँ.
But Bohr's atoms or electrons are also moving.
अच्छा.
They
Oh.
don't emit any radiation.
अच्छा
It's a
अच्छा.
slight contradiction to your EM
हाँ.
theory wave that moving charges have
Hmm.
emission of waves,
EM wave,
EM waves.
yes.
No such orbits where the electrons do not emit any specific radiation because of
Hmm.
motion alone are
Hmm.
known as stationary orbits. So stationary orbits are the orbits where the electrons don't emit any radiation.
Radiation, yes.
Okay? Now the postulates of Bohr, very important. The first question that always comes is the postulates. We've already studied in the form of features, but if they say postulates, you have to
Hmm.
write this.
Okay.
We have already done that. These are the main.
Quantized.
You can study. We've done this.
हाँ.
Quantization of angular momentum.
Yeah.
We've also done this.
Yeah.
We've also done this.
हाँ. हाँ.
ठीक है?
हाँ ठीक है.
Okay, थोड़ा सा जल्दी आ रहा है, but for the timing, just memorize it. You don't need to memorize actually, but finally you will because it's just an expression. So if you want to find the sum of half mv square plus z e square by r, right?
Hmm.
The value is this. The total energy of the electron
हाँ.
after you add the kinetic energy and the potential energy is this. In n orbit, so you can see energy is inversely proportional to n. This is mass of the electron, charge of the electron. This is the atom which is given to you. This is Planck's constant. So energy of an electron in any Bohr orbit with number n is given by this expression.
मतलब जो
Total energy.
इलेक्ट्रोस्टैटिक पोटेंशियल और काइनेटिक
Yes.
एनर्जी को प्लस
Plus
करके.
kinetic energy. So it comes out to be minus 13.6 divided by n square.
Oh, okay.
In short, in electron volts. I will tell you the derivation, don't worry. Okay, just telling you the expression.
Minus.
Yeah, I will, yes, minus. Minus signifies stability. The energy is negative. So kinetic energy is positive, but the
Yeah.
potential energy is negative.
ठीक है.
So this is it. So this is z square by n square, sorry.
अच्छा.
Right, so as z changes, you can put lithium 3, but
Hmm.
n is the orbit. So the energy is also dependent on the atomic number of the atom. Remember, this study was done only for hydrogen. This study is not applicable to all the elements, but only the ones which are hydrogen-like.
अच्छा. Okay.
I will tell you what is the meaning of the hydrogen. Wait for that. Okay. This theory is not applicable to everything in the world. You just put the value of Z. It should be hydrogen-like. Okay. Now, what is the formula of radius, which comes from that electrostatic force coming from the centripetal force? This is the radius. So radius is proportional to n square. If you put the value of h, epsilon, pi, mass of electron, charge, and z, which is generally 1 only because of hydrogen, The answer is this. So for hydrogen, this is your radius of the
अच्छा,
first, where n is equal to 1, right? But if you want to write general expression, what you
yeah.
have to do is R1 is equal to n square and R1. Sorry, Rn.
अच्छा,
Rn is equal to n square R naught,
ठीक है.
which is actually the first orbit, right? R1.
अच्छा, okay,
So you
okay,
can
ठीक.
keep on putting. So if you put n is equal to 1,
हाँ,
you will get the same answer, right?
yeah.
R2, this will become 2 square R naught. This is R naught. I'm saying R naught is this.
Yeah, ठीक है.
मर्जी है आपकी, जो नाम रखना रख लो.
हाँ,
First orbit R naught. We will see how we got this expression. But for the timing, radius is proportional to n square. Okay. Okay. So why was it successful? Because it could explain the atomic spectra. Okay. The emissions which are coming from the atoms, the Bohr was able to successfully tell they are happening because of photon emission and absorption. So if the hydrogen is available as a gas and it is emitting some radiations, you're measuring the
yeah.
how many wavelengths are coming. So you're measuring a
हाँ,
spectra. And then you were able to explain why the emission is happening, because the jumping of electron is happening.
yeah.
Okay. So first, the Balmer series specifically was found out with the help of this theory. Then this theory was also successful in telling the concept of quantized energy levels. That energy cannot be random, but is fixed.
Yes.
This was used later. We don't know. You don't need to know where it was used. Okay. Then it could
ठीक
also
है.
predict the energy levels. That if you transition with this much energy, where will you land at? Because you knew E1 minus E2 is equal to H nu. So if you have 2 electron volts and 2 more electrons volts come to you from the photon, you will land at 4.
ठीक है. हाँ.
E1 minus E2. So all the maths we have written is basically expresses words here. Okay. Now, what are the limitations? Here we will know the hydrogen-like atom. Okay. So any atom which has one electron, you can apply it there only. That's all. Otherwise, this is not applicable. Okay, it could not explain. So hydrogen-like atoms only. One electron, one proton.
हाँ. अच्छा.
Wow.
नहीं, थोड़ा समझ नहीं आया.
No, if you have sodium, sodium will have how many electrons? 12, 11?
Yes.
Won't work. Because then the electrons of the sodium will interact with the uh, nucleus of the nucleus of the sodium will interact with so many electrons, right?
Yeah.
Right. So you can't apply this model there, but you can apply it to lithium 2 plus, because
अच्छा.
lithium 2 plus would leave two. That means 2 electrons have left it. It's only
Yes.
left with 1 electron. So if you want sodium to work in this model, then around 10 electrons need to leave the sodium.
अच्छा, ओके ओके.
Only applicable for
बाद
hydrogen, like means 1 electron.
ठीक है.
Nucleus can be Z equal to 3, but it should not be lithium. It should be lithium 2 plus, which means 2 electrons
अच्छा.
have gone away.
हाँ, या ठीक.
Right? So Z will be there, but it should be mentioned it is hydrogen-like, which means it is understood that it has only 1 electron.
ठीक है.
Okay, you don't need to know this. You don't know what is Zeeman effect. Okay, yeah. He treated electrons as particles, not as wave entities. So he did not think in terms of wave particle duality. He thought it's a particle. That's all. He was not anyway working towards finding out the wave particle duality, right?
ठीक है.
That was not his job. But they say it's a weakness because he did not tell us everything he could. So he could only tell us the particle nature.
हाँ, या.
Right. So these two are good for you. Don't worry about the fine structure and etc. Right?
ठीक है.
And it was incomplete because later on quantum mechanics came, which is more modern physics, which you learn later. So there are more things which got added to Bohr. Even after Bohr, there are other theories. So he could not explain the further developments.
Yeah.
Which is always the truth, right? The
Yeah.
developments will keep on
Yes.
happening. So what's a
Hmm.
okay? But it was a very crucial step in development of the atomic theory.
Acha.
Very,
Okay.
very crucial, right?
Yeah.
He actually was quite close to it. Not
Hmm.
exactly very, very close. Not
Hmm.
the current one, which is a
Hmm.
quantum mechanics theory of atomic theory, but very close to it. So more or less, he developed it. At
हाँ
least the foundation.
ठीक है. Yeah.
Okay. Now we will see how to derive the expression
Hmm.
for the radius, velocity, and energy. There is an expression for radius also. So one is obviously we have already done. So what you do generally is I'll tell you what happens. That will give you a logic also. You don't need to memorize. So you know there is a force acting on the electron, which is the k ze into E by r square.
Yeah.
It's a hydrogen like is equal to
हाँ.
m vn square by rn. So you see the
Yes.
radius of nth orbit and velocity of the nth orbit. So in
हाँ.
this expression, you have both rn
हाँ.
and vn.
Yes.
We want to separately find out independently what is rn and what is vn. We only
Hmm.
want one term. So
Yeah.
you know
Okay.
the quantization of angular momentum,
Yes. Yeah.
right? So I will just
हाँ.
cut this. So this will become rn.
हाँ.
And this will become Vn square is equal to k Ze square upon Rn.
हाँ ठीक है. Yeah.
And an m here because I'm bringing this down.
Yeah. Yeah. ठीक है.
K is Ze square, right? So
Hmm.
now we know, so we want to get rid of one of the variables, V or N. I am
Yeah.
removing, I can remove Rn also, right? So
Hmm.
I will start with this. So what I will do is I will square the two sides. This will become m square Vn square Rn square is equal to n square h square by 2 pi square, squaring the
हाँ.
angular
Yeah.
momentum equation. Now I know the value of Vn square, right? So m
Hmm.
square Rn square into k Ze square by
MRN.
mRn into Rn square is equal to n square h square by
2
2
by
pi
square.
whole square.
हाँ.
I don't know where I've sorry, I've written it again. I've already combined these two, right? M and R.
अच्छा अच्छा. Yeah.
So I'm only replacing Vn square, which is
Hmm. Yes. Yes.
okay. So what I will do now is I have so Rn will go,
Hmm. Yeah.
right? So I will get Rn is equal to n square h square by 4 pi square m square
Hmm.
divided by k
ZD
divided by
square.
z divided by e square.
Hmm. Yeah.
If you solve all of this, you will get
Hmm.
radius is equal to n square 0.529.
Hmm. Yeah. Yeah.
Which
ठीक
is
है.
the expression you memorized.
हाँ. Yeah.
So this is for hydrogen. If you don't,
Hmm.
if you say you have other atomic number, but it is hydrogen like,
Hmm.
put this. Because I
Okay.
had put Z is equal to 1.
Hmm. Yeah.
So you can put Z is equal to anything, right? So this
Hmm.
is Rn with Z existing. Z is not 1, it is Z. So exact formula is n square by Z 0.529. The radius of nth orbit of an element with atomic number Z.
Hmm.
If Z is equal to 1, it becomes hydrogen. Any questions?
Like जैसे अगर जैसे क्वेश्चन में कि सोडियम है
Lithium
बट
3 plus. It is lithium 3 plus, right?
अच्छा
Put Z is
या
equal to 3.
अच्छा Z3 रहेगा ठीक है.
It is hydrogen like, sorry, lithium 2 plus. Z will
ठीक.
be, but orbit number is 1, 2, 3, 4 only.
हाँ या.
That is not dependent on what you are. This total
Hmm.
number of electrons, right? So you write the electronic configuration 2, 1,
Hmm.
SPDF and all that, right?
हाँ हाँ.
Now, if you know the value of R, Put it back here in the value of Vn, which is this. Put the value of Rn here.
कहाँ पे?
Either.
अच्छा, okay, ठीक है.
You will get the radius.
अच्छा.
You had two variables, velocity and radius. You eliminated velocity.
हाँ.
Now you know the velocity. You know the radius. You can find the velocity.
ठीक है.
Right?
Yeah.
So basically, combination of force feature and the angular momentum feature. They were combined to get you expression of velocity and radius.
Yeah.
Got it?
Yeah.
Okay. So the expression, when you solve the expression of velocity, you can memorize this also, right? We can put the values. It will be written in all your books, but you need to just understand it. Okay, so this is the expression you will get for velocity.
So fail to load.
Yeah. Okay. Look at this. Z squared by NH. Got it?
Yeah.
Okay. So combination of angular momentum and force, centripetal force, gives you very good results, radius and velocity in the nth orbit.
Yes.
Okay, now let's come to the derivation of the total energy.
ठीक है.
Let's do that. Okay. Can you see it now?
Yeah.
Okay. So look, this is what I told you.
हाँ.
The total energy is Ke
Yes.
plus P.
हाँ. Yes.
So Ke is equal to half mv square,
Half mv square. Yeah.
right?
हाँ. Right.
And so what he has done is he has put the value of velocity found in the previous derivation
ठीक है. Yeah.
and written kinetic energy as this.
हाँ. Okay.
Okay? Potential energy formula minus KQ1 by R.
ठीक है.
Z is ZE into E. So this is your potential. Now what he has done, he has this R expression we already know. We've already done the derivation, right? So he has substituted the value of the radius also. So kinetic energy, if you divide these two after the substitution, this and this, after you substitute velocity in this and radius in this, the potential energy has become this. If you divide these two, which is this expression, this one and this one. Sorry, this one and this one. You will find that kinetic energy is negative half of PE. So if your potential energy is, for example, minus 27.2, example, right? Because it's a multiple of 13.6, minus 27.2 electron volts. This is your potential energy, negative.
Yeah.
You want to find kinetic energy, it's very simple. Kinetic energy will be equal to minus half into minus 27.2.
अच्छा, okay.
This will become 13.6 electron volts.
अच्छा, okay.
So if you're given the values, you can easily find. So if I tell you kinetic energy is given to be X, what is the potential energy? Very simple.
Minus 2x.
Minus half X. What is the total energy? X minus half X is equal to half X. Right? So the total energy is half times kinetic energy.
अच्छा, okay.
So there, and potential kinetic energy is also potential energy is minus half times Ke.
अच्छा, okay.
Right? PE is
हाँ
minus half times KE.
हाँ
And total energy, sorry, I think I'm saying the reverse.
हाँ 2x like डबल होना चाहिए ना.
Double होगा, right? Double
हम्म,
होगा. So the formula is this, right? KE is half of PE. Sorry,
हाँ.
with a negative sign. And total energy is plus half PE
Yeah.
because the expression gets cancelled.
हम्म.
Okay. आगे समझ में नहीं आया?
नहीं आ गया.
Okay. So total energy is half KE and
हाँ.
KE is minus half PE.
Yes.
Finished.
अच्छा.
Bohr model is finished. We have not done atomic spectra right now. So
हम्म.
I will not move forward. I have covered so many things by now.
Yeah.
Go back and digest it, all the formulas,
ठीक है. Yeah.
derivation, this, that,
Yeah.
etc., etc.
Okay.
And what I will do next time is I will do numericals
हाँ.
on this, few
अच्छा.
numericals on this, like
Okay.
find the radius, find the velocity. If the orbit becomes double, what is the new velocity? If the
हम्म.
atomic number is 12, it's
हाँ.
hydrogen-like, then we'll see different types
Okay.
of solutions in this.
ठीक है.
Go back and memorize Bohr model. What is Bohr model? I will do numericals on what we have covered: radius,
हम्म.
velocity, energy, angular momentum, and I will do atomic spectra. What we have not done is a key feature, which is a movement of electron from one orbit to another, resulting in emission of the atomic spectra. And lines called as Balmer line series,
हाँ. Yeah.
Lyman series. We have not done that.
Yeah.
Paschen, etc., etc. So we will cover both. But I will
ठीक.
stop here so that you go back and revise it first.
Okay.
If you've done chemistry thoroughly in class 11th, you will quickly be. Chemistry is not actually, dealing with centripetal force and all of that. It doesn't.
Yeah.
So, but it does deal with energy. So maybe energy expression is familiar. And this is, if you solve all of this, right? The total energies, look at this. Total energy. Sorry, this is this is your total energy. Negative sign implies it's a stability. If potential energy is -2,
हाँ.
then the kinetic energy is +1. So
Yeah.
total energy remains negative.
Yeah.
If this is your total energy, you want to find the kinetic energy.
Uh-huh.
Right? If this is your total energy, and you know that the kinetic energy is given by minus half PE, right?
Yeah.
Total energy is given by half of what? KE. No,
Children.
half of PE, but with positive sign,
अच्छा.
right? So this is your total kinetic energy, which is known to you,
हाँ.
right? Make it like this.
अच्छा.
It is equal to half of PE, right?
हाँ. Yeah.
Take 2 on the other side, you will get PE is minus 27.2 by n square.
अच्छा.
And if you put a negative sign in front of this thing, you will get your kinetic energy. Kinetic energy is this, right?
Yeah.
Minus minus will become
हाँ.
plus.
Plus. Yeah.
So from each other you can find, right? If one is known, the
Yeah.
other two can be found by ratio or proportion.
Yes.
Okay, go back and revise all of these. And
All
what
right.
we will do tomorrow is do numericals on this and the atomic spectra, the
ठीक.
line series.
ठीक है.
ठीक है, वो अपने आप में थोड़ा लंबा टॉपिक है, तो you need to
हाँ.
focus on that also. It's a separate topic.